Okay, here we are ready to do a ray tracing diagram. Now the idea is, first of all, we have an object. Let's say our object is way out here. And I've marked the center of curvature and the focal point. The distance between the focal point and the mirror is called the focal length, and the distance between the center of curvature and the mirror is the radius of curvature. And there's a relationship: the focal length is half of the radius of curvature. And in fact, when I drew this mirror, I just took a compass, made a little circle segment, and counted out the half the distance is the focal point. Now the idea here with ray tracing diagrams is that when you've got an object, the object has light shining on it from somewhere, we don't care where, and light is reflecting off of this object in every possible direction. And that's important because if light is going in every possible direction, we can pick rays of light that are relatively easy to follow or to draw, and they go to the mirror and then come back, and somewhere in there is an image. So we're trying to figure out where the image is, and the way we do that is we trace the rays to the mirror, off of the mirror, and then wherever those reflected rays intersect, we know we have our image. Now, for clarity's sake, I'm going to use different colored pencils as I trace my rays here. You certainly don't have to. In fact, because they get dull and make awfully thick lines, it may be an idea that you don't want to. So there's 3 reference rays, and they're listed in your book, and there's diagrams and stuff in your text as well. But I want to show you the actual process. So you've got your object. One of the reference rays is that any ray that comes into the mirror parallel to the principal axis is reflected through the focal point. So one of the rays coming off of this object is parallel to the principal axis. Strikes the mirror right there. And then I'm going to put my pencil right there and put the, that's the focal point. This is where it strikes the mirror, and I just go in a straight line. And we draw an arrow to show that that's the actual reflected ray. Another ray of light is from the object through the center of curvature will go right back along itself. And that's because any radius is perpendicular to the surface of the circle, and since this is going through the center of curvature, by definition it's a segment that includes a radius right here. Angle of reflection is equal to the angle of incidence. It's perpendicular, which means the angle of incidence is 0, so the angle of reflection is 0, blah, blah, blah. Put my pencil at the tip of the arrow, same point that my first line was from. Put my pencil tip at the center of curvature, making sure that when I trace it, that looks good. That looks good. And hits the mirror, bounces straight back. Now you can see we've got 2 reflected rays here, and they cross at this point. Now, again, with the one through the center of curvature, it's the same as the incident angle. That's fine. We would also have a third line. The third reference ray would be from the tip of the arrow through the focal point to the mirror. Any ray through the focal point, incident through the focal point, is reflected parallel. And I kind of got lucky here with the size of my image, and I'm going to put my pencil tip where it strikes the mirror, like that. And for these, I'm just going to eyeball it. It's pretty much dead on that line, though. And I'm going to go like that. Now, in an ideal world, and I got lucky here, all three of these rays, the one parallel through the focal point, through the center of curvature, back along itself, through the focal point and out parallel, they would all intersect at the same place. And they do in this particular example. Again, that's more luck than anything else. Now, these three rays came from the tip of the object. And the object is between that point and the principal axis. And the same thing is true of the image. So here's the tip, like that, and it goes downward in this case. Now you notice these three reflected rays actually intersect right there. So that makes this a real image. It is inverted or upside down. And if you look here, this is 2 boxes high, this is 1 box high. So it is smaller than the object. And all of these follow that same basic principle. There's some variations because when you get the object, say, inside the center of curvature, you can't really use that ray as easily. It's possible sometimes. And once you get inside the focal point, it gets a little more complicated still. But we'll go over that in another video.
Now, here you see exactly what we had before, except this is, rather than a drawing, it's the actual real thing. And you've got the object, which is a yellow arrow. It's a little foreshortened because we're looking at it from the top. You can see the blue arrows represent going from left to right, the center of curvature, and then the focal point of the mirror. Now those are approximate, they're not perfect, but here's the actual geometry that we're talking about in the example you just saw. And here we are looking at the actual image of the object as well as the object in the mirror. This is what we're trying to predict by doing the ray tracing diagrams. You can see a couple things pretty clearly. First of all, the image is in the opposite direction to the object. The object is pointing to the left, the image is pointing to the right. The image is also smaller along the left to right axis. Now, because this is a cylindrical mirror, in principle, the height of the object would be equal to the height of the image because it's not changing anything, but it looks smaller because the image is further away than the object is.